All right. So I want you guys to suppose with me for a little bit. Suppose a large bag of Reese's Pieces has 1,000 pieces in it. The manufacturer says that exactly 40% of the candies are orange, and that is a true statistic from them. I don't remember who the candy company is. I don't remember if it's, I think it's Hershey that makes them. I don't remember. But they say 40% of the candies in Reese's Pieces are orange. If we selected a sample of 50 pieces out of this bag that has 1,000 pieces of candy in it, how many will be orange? That's what we're going to try to answer today. Let X be a random variable. It is the number of orange candies in the sample. Explain why X is a binomial random variable. What do we have to check to see if it is a binomial random variable? Bins. What's the B stand for? Binary. I. Independence. N. Number of trials is fixed. And then S. Same probability of success for each trial. So, is this binary? Yes. What would success be here? Orange. And failure? Not orange. Are we independent? How do we decide if we're independent here? Are we sampling with replacement? Are we going to put the candies back after we've had our hands all over them? Please don't. Don't take 50 candies out and get your germs all over them, then put them back in the bag. So we're not sampling with replacement, which means we're not independent. How do we get around that? 10% rule. What would I be checking? Than the entire population, yes. How many pieces are we going to sample? 50 out of 1,000. Is 50 less than 10% of 1,000? Yes. What is 10% of 1,000? 100. So we get our 10% rule. 50 is less than 10% of 1,000. So even though it's sampling without replacement, we can still get our independence this way with the 10% condition. Is the number of trials fixed? Yes. What is our number of trials? What's lowercase n? 50. Same probability of success for each trial. What's the probability of successfully getting an orange candy? 0.40, yes. So this would be my explanation for why X is a binomial random variable. We are going to simulate choosing 50 candies out of 1,000 candies. This is what we're going to need your technology for. I don't have enough money to buy a ton of Reese's Pieces for everybody, so that's why we're going to use the online simulator. All right. So if you are still sitting on the Canvas page, I need you to scroll down just a little bit. We're going to click here where it says Rossmann Chance Applet Collection. And it should take you to this. You should see what looks like a candy machine that's like in the entryway to Kroger or something sitting here. And it's full of Reese's Pieces. What did we say the probability of an orange candy was? 40%. So I need to change this from 0.5 to 0.4. How many candies did we say we were going to select? 50, so I need to change this to 50. And for my example up here, I'm going to pull one sample so you can see what's happening. Then I'll give you directions as far as exactly what I want you guys to do. So I'm going to pull one sample right now. I'm going to leave the animation on. When you're doing this on your own, you might want to skip the animation because it goes a lot faster when you skip the animation. This is going to pull a sample of 50. And it's separating out the orange from the not orange candies. And so it tells me right here, the number of orange candies that I got was 25. And if you scroll down a little bit, it starts to make a dot plot for you. So you can do this lots and lots of times. What I want you guys to do is I want you to take a random sample of 50 Reese's Pieces, but you're going to do this a total of 5 times. So you can tell it to pull all 5 samples, or you can do the samples one at a time. Like I said, it goes faster if you turn the animation off. But you want to pull 5 random samples and have the number of orange candies in each of those random samples. And then you're going to come up and add your 5 values to this dot plot up here, just like we did the other day. All right, so I want you guys to copy that to the best of your ability into your notes. What does each one of those dots represent? The number of orange. That's not wrong, but it's not fully complete yet. Add on to it. The number of orange candies in a sample of 50. How was the sample of 50 selected? Randomly. So the number of orange candies in a random sample of 50 Reese's Pieces. Oops. Get in a little closer here. There we go. 1 sample of 50 candies and the number of orange Reese's Pieces in that sample. Or you could say the number of orange Reese's Pieces in a random sample of 50 candies. How did we say this was distributed? Up on number 1, we said this was a binomial random variable. How do you find the mean for a binomial random variable? What'd you say? N times P, yes. What was our N here? 50. What was P? 0.40. Go ahead and calculate, after you get this into your notes, down on number 5, I want you to calculate the mean, and I want you to calculate the standard deviation. You can pull out your formula sheets if you need to. And once you get this sketched into your notes, I want you to go down to number 5 and calculate the mean and the standard deviation. Is there anybody still working on getting the dot plot into their notes? Okay. I'm going to flip over to the next screen then, if you guys are okay with that. What is the mean here? 20. N times P, 50 times 0.40 gives us 20. What is our standard deviation? 3.464. Remember, that's N times P times 1 minus P, all underneath the square root. So we have 50 times 0.40 times 0.60 underneath the radical, 3.464. So we said that this was distributed as a binomial random variable. What is the approximate shape of this distribution? It's approximately normal. How can we check that to see if it actually is approximately normal? Does anybody remember what we check? We want to look at large counts. Does anybody remember how to check large counts? N times P has to be 10 or bigger. Was N times P 10 or bigger here? Yes. N times P came out to be what? Came out to be 20. So that was bigger than 10. What else do I have to check? Not just N times P, but yes, N times 1 minus P. So if I do N times 1 minus P, I would do 50 times 0.60, which would come out to what? 30, which is bigger than 10. If N times P is greater than or equal to 10, and N times 1 minus P is greater than or equal to 10, then we can say that our shape is approximately normal. So this right here would be our justification, and then it said we need to sketch it also. What pieces of information does my sketch have to have? Needs to have the mean and standard deviation. What letter do you have to make sure to include? N. So your sketch should look something like this. Make sure that right down the center of your sketch you have that mean of 20. So far, so good? All right, let's flip the page over. Over to page 10. That does not conclude everything we're doing. Instead of finding the number of candies that are orange, I want to practice with one of the things that we've been talking about, and I want to find the proportion of candies that are orange. So I want you to use your sample of 5 numbers that you wrote down on the other side of the page, and we're going to turn each of those into a proportion, into a p hat. What do you need to do to each of those numbers to turn them into a proportion? Divide them by 50 is absolutely correct. So take each of those numbers, divide them by 50, and you will write them down on this line. So you're going to have 5 different p hat values. once you have those 5 proportions, we're going to come up here and make another dot plot. What does each of those dots represent? Absolutely, the proportion of orange candies in a random sample of 50 candies. Or another way to word that is one sample of 50 candies and the proportion of orange Reese's Pieces in that sample. So same idea, more words, but exact same idea. This is a sampling distribution of p hat. Why did I say this was a sampling distribution of p hat? Because it's based on our samples. These are proportions from our samples, yes. I would like for you to get this sampling distribution into your notes. What do you think the mean of this distribution is? What was the mean of our other distribution when we did n times p? It was 0.4 times 50, right? So we had 20 as our old mean for our distribution. Now these are proportions. And what did we do to get each of these p hats? Divided by 50. So what do you think we could do to the mean? Divided by 50. What happens when you do 20 divided by 50? You get 0.4 or 0.40. How do you think we should find the new standard deviation? What do you think we could do to find the standard deviation for this? Divide that by 50. So I would like you guys to calculate the new mean and the new standard deviation down on number 11. You guys okay if I go to the next screen? Is anybody still working on the sampling distribution? What do you notice, before we go on and answer any other questions? I know I changed the dot size because we went way above on this one. I didn't want to run off the screen on the other one. But what do you notice about the overall shape between here and here? pretty much the same. I think if I hadn't changed the dot size, they would be exactly the same. When I changed the dot size, I think we got a little bit confused, and that's totally fine and understandable. But we have pretty much the exact same distribution here, or shape of the distribution. This guy back here was my sampling distribution of X. We said our new mean, old mean divided by 50 is 0.40. And we calculated that mean, the original mean, by doing n times p, right? And then if we divide by 50, I'm dividing by n, right? We did n times p to get the numerator, but then that denominator is n. So those are just going to cancel out. The mean for my sampling distribution of p hat is just whatever p is. What did you guys get for the new standard deviation? Yes. 0.069. I took it out one more decimal place, but if you left it at 0.069, that's perfectly fine. So I want to think through how we arrive at this. How did we get that 3.464 again? Standard deviation formula. What was that? Square root of n times p times 1 minus p. And then we took that and divided it by 50, right? So that's going to look like this. But I feel like there's a way to clean this up a little bit, because see how I have n underneath the radical here and I have n down here? And you can do that. That'll give you the right answer. But there is a way to clean this up, and you're not going to see it like this on the formula sheet. They're going to have the cleaned up version. What would I have to do to this n if I wanted to put it underneath the radical? Square it, right? Because the square root of n squared is n. So if I wanted to put it underneath the radical, I need to square it. So I could have the square root of the fraction n times p times 1 minus p over n squared. And then this n in my numerator cancels out with one of the n's in my denominator. So my standard deviation formula for p hat is the square root of the fraction p times 1 minus p over n. We are going to pause right there, because I promised you guys I'd pass back your tests today so you could see those. We will pick up here tomorrow. If we don't get all the way done with this and the next lesson, then that'll bump the homework to being due on Friday. But I'll let you guys know at the end of class tomorrow whether homework is due Thursday or Friday.